Example 3. And again, this is a cantilever beam carrying distributed load W as shown in the figure. And the beam is fixed at the left end and it's supported by a roller at B. However, there is a 3 millimeter gap between the beam and the roller B. And determine the reaction force at roller B. I know that in the previous chapters, apart from indeterminate problems, another type of confusive problems involve gaps. Unfortunately, in this example, we have both indeterminate beams and gap. Will this combination of two confusive problems make this problem super confusive? The answer is no. Okay, I will show you why I said no. Okay. Okay, so first of all, to solve this problem, how should we deal with the gap? This is our first question, right? So how shall we deal with the gap? Right, this is a big question, but let's hold it here. Okay, let's hold it here, and then let's focus on the point B. Since we're requested to calculate the reaction force at the roller B, so we just focus on point B and ignoring the gap. Okay, the logic is simple. Since to make this problem meaningful, the W has to be large enough so that it can generate a large enough deflection at point B, and the cantilever touch the roller at point B, and there's the reaction force generated at point B. Otherwise, this problem will lose its meaning, right? So if that is the case, and we ignore the gap, so here this overall thing can be splitted into, or can be simplified as concentrated load W through AC, and we have a reaction force By. Okay, this can be simplified into this case if we ignore the gap. Okay, this is the point A, point B, and the point C. Okay, we have done with the first step according to the general algorithm. Okay, step number two is to split it into simpler parts. Okay, this one equals the first case will be just distributed load. Right, the cantilever beam subjected to W, and so we're calculating the deflection at point B, delta B1. Okay, and in the beam 2, it will be a cantilever beam subjected to By. Then it will be deformed in this way. It will be deformed in such a manner so we can calculate delta B2. Okay, this is how we split this case into simpler parts. We got a beam 1 and a beam 2. Right? This is the beam 1, and here is our beam 2. Okay. Or in this case, we have beam 1 and beam 2. Okay, just two simple cases. Then it will be our step 3 again. Right, this is our step 3. We just solve the delta B1 and delta B2 in these two simpler beams. Right? In beam 1, In beam 1, it's a cantilever beam subjected to a distributed load, and we're calculating the deflection not at the free end, it's at x. Right? So in our table, you can see this will be our this case, and you need to use equation 30 since we're calculating deflection at x, not the maximum value. Okay, so we'll use equation 30. So the delta B1 can be calculated using equation number 30. That will be Wx squared over 24 EI by 6L squared minus 4LX plus x squared. This is our equation 30. Okay, then what is the x here? In beam 1, what is the x? Right, the x in this case equals LAB. Equals LAB, that is 5.8 meter or 5,800 millimeter. We need to do this transition because you can see here what is given. You have millimeter here, and the force is given the Newton, kilonewton, right? It's a meter. Right? So we need to keep everything consistent since you have different units. So we tend to use millimeter, Newton, and MPa in these calculations. Okay, so we convert these meters into millimeters. Now, what is L? What is L? Since the distributed load is applied through the whole beam, so the L should be AC or AB plus BC. Right, this is L AC. Well, that is 5.8 plus 1.8. That is 7.6 meter or 7,600 millimeter. Okay, using these numbers, we can calculate the delta B1. So that the W will be 65 kilonewton per meter, or just 65 Newton per millimeter. Right, so you will have 65 by the x, 5,800 square over 24 by the E is 300, but you need to add 1,000 because you need to convert gigapascal into MPa. Right, so by the I it's 343 million millimeter to the fourth. Right, by 6 times 7,600 square minus 4 times L 7600 times x, that is 5800 plus 5800 square. Okay, then the result here is 180.5 millimeter. Wait, this is beam 1, and then let's look at beam 2. Okay, in beam 2, this cantilever, the same cantilever, is subjected to a BY at point B. Okay, again, as we analyzed it before, you just when you have the BY, this part AB will be bended, but the section BC will actually keep straight. This will not be bended. So if you're caring about the deflection at point C, you can use the triangle and the slope at point B to calculate an additional component. But here, since we're only calculating the deflection at point B, so this section BC will be useless. Okay, we only calculate. We only calculate the part AB. Okay, so here in this beam 2, the delta B2 can be calculated. You need to select the equation. Right, this is I believe it's 20. Okay, we're calculating the maximum deflection in cantilever section AB. So we just use the maximum deflection equation. So this is PL cube over 3EI. And in this case, the P, of course, it will be BY, and the L is LAB. Right, it is 5,800 millimeter. Okay, so to extend this equation, you will get BY by 5,800 cube over 3 times 300,000, right? Transforming gigapascal into MPa, multiply 343 million. Okay, here you will get BY over 1582. Of course, here we use the equation 20. Okay, so far we're done with step 3. Okay, then later we're coming to step 4 to analyze the compatibility. At point B again. What is the compatibility equation? So here we just need to consider the gap at this point. So under the under the distributed load W. So under W, since you have this gap of the 3 millimeter, the beam can deflect at if you add this W to this cantilever beam, the cantilever can deflect at point B for 3 millimeter. That is the gap, right? It can deflect at point B for 3 millimeter before touching the before touching the roller. Okay, so this is the key to write the compatibility equation. So let me ask you this: since this additional deflection happens to this cantilever when you add the W, so in this component B1 and B2, delta B1 and delta B2, which one is bigger? Which one is bigger? Okay, since the B1, let's look at here. The cantilever can deflect under W, that is the B1, right? So B1 can be equal to 3 millimeter, while the delta B2 is still 0. Okay, so that is to say that delta B1 is always larger than delta B2. We're talking about the magnitude, right? Not directions, not considering directions. Whereas the magnitude of the delta B1 will always be larger than the delta B2 by 3 millimeter. Okay, so just based on this equation, based on this analysis, we can write this equation. Okay, delta B1 minus delta B2 equals 3 millimeter. Okay, the magnitude values. Or you can write that delta B1 equals delta B2 plus 3 millimeter. Right. So if you do the calculations with signs, right, with signs, you can also write delta B1 plus delta P2 equals 3. Right. You will get actually the same equations as the first one. Okay. If we just use this one, and use the result we just obtained, you get a delta B1 is 180.5 minus by over 1582 equals 3. So here you can derive that the by equals 281 kilonewton.